good afternoon, good night, good evening, wherever you join us from. I'd like to welcome everyone to the 7th webinar of the WCRP Digital Earth's Lighthouse Activity webinar series. My name is Rosimar Rios-Berrios from the National Science Foundation National Center for Atmospheric Research in Boulder, Colorado, and I'll be one of their moderators today. This webinar series is part of the WCRP Digital Earth's Lighthouse activity. The aim of this series is to help maintain more regular and open dialogue between active researchers and users on the development and evaluation of kilometer-scale global and large domain models across the world. We plan to hold seminars every 2 months, spanning a range of groups working on kilometer-scale modeling around the world. And you can find a recording of the previous events via the webinar website. The focus for today is on the experience from the Bureau of Meteorology in Australia in exploring the value of larger domain kilometer scale models in their model development and evaluation, and the work of Charmaine Franklin and colleagues in Australia. And before we get started, I will pass it on to our other moderator today, James Warner.
No, warm welcome from my side. I'm James Warner from the UK Met Office. Before I introduce our speakers, I've just provided an overview of today's events and modes for interaction. So our various speakers will provide a combined talk before we close with the Q&A session. So during the talk, feel free to post questions using the Q&A feature at the bottom of the Zoom window. You can upvote the questions posted there with the thumbs up icon to highlight which questions you'd wish for us to get to earlier in the Q&A. Please reserve the chat function for technical issues related to the webinar and use the Q&A questions to the presenter. We will then get to these questions in a discussion session following the presentation. I trust we have lots of interaction through the chat today. Please feel free to post in the Q&A. It'd be great to get lots of comments and questions in the chat. For the presenter, we'll give you a warning with about 5 minutes left, and when there's 1 minute left for you to wrap up. We're also expecting that today the recording will be made available via the WCRP website over the next few weeks.
And now it's my turn to introduce the speakers. So today's webinar, as I mentioned, will introduce some of the work happening at the Bureau of Meteorology, Australia's national weather, climate, and water agency. The Bureau plays a critical role in delivering accurate, timely, and reliable weather forecasts and climate outlooks, which are essential for protecting lives, property, and our environment. Today's speakers are from the Bureau's research program, which conducts research to develop weather and climate models, improving the accuracy of predictions and our understanding of atmospheric processes and Australian weather and climate. Over the past few years, the focus of the Bureau's model development has been on large domain pan-Australia convective scale weather and climate modeling, with the goal of capturing fine-scale atmospheric processes such as convection and cloud dynamics, as well as representing the larger scale influences. This work is important in addressing challenges posed by extreme weather events and climate change, particularly as we work to improve predictions across the Australian continent, spanning both tropical and mid-latitude regions. And with that, we welcome Charmaine and colleagues to lead the presentation. The floor is yours.
Thank you very much for the introduction, and thank you for the opportunity to give this presentation. So I'm going to start us off, and I'm going to introduce you to some of the type of weather that we have in Australia and the motivations behind generating and developing these convective scale models. Next slide, please, Susan. So Australia is the 6th largest country. The country spans 35 degrees of latitude and has 35,000 kilometres of coastline. And with such a big country, we have a wide range of climates, ranging from the wet monsoon or tropics in the north to the arid and desert region in the centre of the country. And then in the south, we have a temperate zone with very much 4 distinct seasons in the south. And the type of weather patterns in Australia that lead to severe weather includes tropical cyclones, monsoon lows, deep low pressure systems that we call east coast lows. We have really vigorous squally type of cold fronts and complex low pressure systems. We also experience these broad, moist northwest cloud bands that extend from the tropics to southern Australia, causing a lot of widespread heavy rain. We also have cold air outbreaks that come up from Antarctica over the Southern Ocean. Next slide, please. So the type of weather hazards that we need to provide predictions both on weather and climate timescales for heavy rain and floods, damaging winds, hail, lightning, and we do have tornadoes in Australia, fog, we have bushfires every summer and heat waves, air quality events, and we do also have blizzards in the winters on our Alps. And so there's an escalating demand for improved modelling and prediction of these severe weather hazards around the country. And that increasing demand is also coming from an increasing range of sectors from around the country. Next slide, thanks. So some of the benefits that we see from running the models at these kilometre scales or convective scales, the first big one is around the explicit representation of convection in the models. So we see that turning off the convection scheme produces an improved diurnal cycle, more realistic rain rates. We have coastal convection that can propagate realistically inland, which is a problem in our global models, for example. And we also represent convective organisation and the outflows and back-building associated with that. Tropical cyclones are represented more realistically, particularly the intensity of those cyclones and the extreme wind gusts. The other benefit of running the models at these higher convective scale resolutions is that we better represent the local topography and surface characteristics. And so we see improvements in the orographic precipitation, land-sea breeze circulations, elevated heating, cooling in the valleys, and therefore the localised fog and air quality. And so in Australia and at the Bureau, we use, the model that we use is the UK Met Office Unified Model with joules as the land surface. And in Australia, we call this modelling system ACCESS, which is the Australian Community Climate and Earth System Simulator. So you'll hear the word ACCESS quite a bit throughout this webinar. So it's essentially the unified model with joules. And so our ACCESS convective scale models really do deliver this improved guidance to better predict local hazards. And they're also used to drive and support downstream models for a range of different applications, including flooding and stream flow, fire danger, air quality, solar and wind energy forecasting, and aviation. Next slide. So as well as lots of benefits of running the model at kilometre scales, there's also lots of challenges. So a big one is that we're only partially resolving convection, and when we run the model at higher resolutions at these sub-kilometre scales, we're only partially resolving the turbulence. So we're in the grey zones. These models are computationally expensive, so we do need to play a bit of a game around finding the balance between the domain size and resolution. We need to worry about how we represent uncertainties, both in the initial and boundary conditions and the model error. And so we typically do that by running ensembles. And you can see the need for running ensembles from those figures on the bottom there, which is 3 ensemble members all simulating a tropical score line. And while they all have deep convection, there's only one in the centre there that actually forms a score line. So really important to be thinking about ensembles in convective scale modelling. We also need to develop the appropriate metrics and evaluation tools to evaluate convective scale models. And we need high resolution observations, both to initialise our models and also for that evaluation work as well. And so now I'm going to hand over to Belinda Roux, who's going to introduce our Pan-Australia ACCESS NWP model and introduce you to the site's configuration. Thanks, Belinda.
Thanks, Jermaine. So currently the Bureau have 7 1.5 kilometre resolution operational numerical weather prediction model domains covering the most populated areas. These domains you can see on the map on the right. So there's a desire to have high resolution forecast nationally, and there's lots of benefits having, like Jermaine mentioned, both convective scale and also having a single domain for us. One of the potential benefits for a single large domain is that you can capture the scale interactions, so the upscale influence of the tropical convection on weather in the tropics and extratropics, which may produce more skillful forecasts of local extreme precipitation. So Axis A is a model covering the whole of Australia. It is a 1.5 kilometer horizontal grid spacing, 90 vertical levels. We do use variable resolution grid to deal with the spin-off effects at the boundaries. The full domain is quite big. It's more than 1 billion points, grid points. And we run the model out to 48 hours of lead time. Thanks, Susan. You can move on. So for our science configuration, we use the regional atmosphere and land configuration, RL 3.2. It's a unified mid-latitude and tropical configuration, which is one of the requirements we had because Australia spans both the tropics and the mid-latitudes, which is really nice. It's the RL3 is the first configuration that had the combined one. So it includes double moment cloud microphysics scheme, which is CASIM, and the new bimodal cloud cover scheme. We've also used higher resolution and more recent data sets to define the surface properties, such as a more realistic representation of the urban areas, and we're also using the more complex urban scheme Mauritius. Just the image on the right is one of our cases with the air temperature over the whole of Australia, and the insert is over Melbourne, which is one of our urban areas. So the RL3 generally gives more realistic precipitation distributions and cloud properties. It still does have the degradation of the near surface cold temperature bias, but the winds are, 10-meter wind speeds are generally reduced better, particularly the nocturnal winds. So overall, the RL3 tends to be better than its predecessors. You can move on, Susan. So in testing the model over Australia, we have run a number of case studies and short trials. So first we tested the model boundaries, looking at XTC, UAC, and Seroja for TC Seroja, which testing the eastern and western boundaries, and Hailstorm with convection, testing the northern boundaries, where we have some steep topography over PNG. The image on the right is an image of tropical cyclone Seroja, which crossed the western boundary, and it was quite a severe tropical cyclone. When at landfall, it was at the category 3 strength. We're also testing some extreme conditions like extreme heat, rain, winter weather. We looked at fog and visibility, convection in the tropics and subtropics, and we tested fixes for known issues as well. In all of these tests we've done so far, I must say, the results look very positive. So you can move on, Susan. So this is just showing 2 case studies for what we looked at. The first one is the Perth fog, which was one of our first cases we ran. So the RL3 uses climatological aerosols for its visibility diagnostic, and Australia has very clean air climatologically. The middle top image showed the climatological aerosols over Australia, and it's quite low, which can lead to higher visibilities. So the top left corner shows the Himawari 8 image of the fog and low cloud, night microphysics. So the cyan color is the fog. It was quite a widespread event over Western Australia. Lasted western part of Western Australia. Lasted quite a half a day or so. So the single aerosol number can give some what binary behavior in the visibility. So in the bottom left is the minimum visibility for the event, with the red colors in up to 1 kilometer, and then the bluish colors more than 10 kilometers. So, but if you look at the fog fraction, which is the image next to it, the model has done a pretty good job in getting the fog event over the area. So we often focus on extreme events or significant events, but one of the nice things about the large domain is we can also look at more benign events. So in March 2021, there was the tropical Saraja to the west of the country, but the east had quite benign weather. So we used that to look at just some urban effects over Sydney. The time series on the top left show the temperature and dew point temperature at Sydney Airport. There's quite good agreement between the model and there's a slight under focus of the max temperatures at Sydney Airport. There's a good timing in a drop in the dew point temperature. The higher temperatures, higher dew point temperatures are possibly linked to a known soil moisture issue over the urban areas. And then in the bottom, you can just see a loop of the screen temperatures over the Sydney region with the observations overplotted in the dots. And again, the model captured it very well. Thanks, Susan. You can move to the next slide. So we both looked at case studies, and then we also had a verification of all the cases, all the trials, and just showing two regions, which is the tropics of Australia and Southeast Australia. Because Australia is so big, you have to verify it over different regions as well. So you can see the precipitation, which is the distributions to two big images. There's quite a bit difference depending on where you are. In the tropics, the rainfall is slightly underestimated in Axis A in the lighter rain rates. Then the median rain rates slightly over and quite good for the high rain rates. Whereas in Southeast Australia, it's the other way around. So it's slightly overestimated in lighter rates and then underestimated in the high rain rates. Above that is just the mean error for the 10-meter winds speed. And again, you see that there's a difference between the two regions. They're both fairly good, but in the tropics, there's a bit of a overestimated at certain times and then slightly underestimated other times. And whereas in Southeast Australia, it's slightly underestimated in general. And you also see the diurnal cycle in there. Thank you, Susan. You can move to the next slide. So just in summary, we're developing a national high-resolution 1.5 kilometer NWP model for Australia using RL3 science. Some of the main findings from our science evaluation is that it does produce more realistic precipitation distributions in RL 3.2 with fewer overestimations of heavy rain and increased light rain. It's an improved representation of convection, but we're still seeing too many small rain cells with rates exceeding 4 millimeters an hour compared to GPM. But rain cells with effective radius of more than 50 kilometers compare well to GPM. So there's generally small biases in temperature and winds. The temperatures tend to be biased low during the night. And for the rest, like I said, there's a bit of a difference depending on the weather, on the region you're looking at. But we did see in our case studies, we didn't see the excessive snow accumulation and cold temperatures that was reported by some other groups, some other RL3 evaluations. That's why we did one of our winter cases, but we did not see that in our case. That was actually quite good. So next, Susan Rennie will talk about the data assimilation implementation in Axis A.
Thanks, Belinda. So we took the forecast configuration that was developed, which Belinda just presented, and we've incorporated it into a full cycling NWP suite. This is running with an hourly 4D VAR on a linearization state grid of about 4.5 kilometers. We're simulating a wide range of conventional radar and satellite observations. We are incorporating radar reflectivity and Himawari clear sky and all sky radiances for the first time in this system. We also have land DA to adjust the soil temperature and moisture using an ensemble Kalman filter. We've included large-scale blending, note the reference there that the Met Office has developed to incorporate information from the parent model every 6 hours, where we run a short downscaler and then create an increment filtering out the smaller scale features and essentially assimilate that into the system. This provides quite a large benefit. Access-A will also support our national analysis system, which is a low latency analysis product produced using a 3D VAR, which is much faster to run. This will provide better situational awareness for our forecasters. There are a lot of challenges to continental scale DA. The size is definitely one of them. The computational cost and the data volumes that need to be handled by the supercomputing system can make it challenging to fit an operational schedule when you're running an hourly cycling system. In Australia, we also have very uneven observation coverage, as shown here on the right. The surface observation network is very sparse in the centre of Australia. Our Access-C systems, the smaller domains, cover the high-density areas, which have much better observation coverage, but now Access-A is simulating the inner areas of the continent where we have very few observations, and this can also be challenging for the quality control of isolated observations when there's nothing nearby to compare it to. We also have very few radio sondes, and many areas are outside of the common aircraft flight paths. Additionally, there is limited satellite observations. Hourly cycling system means that satellite observations may not arrive in time. Therefore, it is critical to have local reception of satellite observations. Otherwise, we wouldn't have any satellite observations at all. I'll talk a bit more about satellite DA. The satellite footprints are generally much larger than the 1.5 kilometre model grid. And this isn't actually taken into account when we're assimilating it. Satellites can also have biases that are latitude dependent, and Access-A covers a large range of latitudes. As noted, the orbiting satellites only provide data a couple of times a day, so there are often cycles which don't have any satellite coverage from the orbiting satellites. The Bureau has done some thinning experiments and found that thinning the satellite data to 70 kilometres gave the best benefit, as noted by the Hinton diagrams down the bottom here. However, 70 kilometres is obviously much coarser than the model grid of 1.5 kilometres, so there may be ways to improve how we simulate satellite observations to make better use of denser information. Our current status is that we've almost completed running 3-month summer and winter trials for the initial assessments. This is the first time we've got near close to the full final science configuration, and we're running for an extended period, which will give us the opportunity to assess how the model performs over a long period, have enough data for a full statistical assessment, and also look for any drifts or trends in the model. I've just included a time series here as an example. As you can see, it doesn't quite get to the end of February, so we're quite close to the end of the 3-month period. With this data set that's being produced, we're allowing users to explore any benefits that can be gained from modelling the whole continent, which could include things like solar nowcasting, hydrological modelling, and severe weather. One of the advantages is that Access-A now covers a lot of our mining areas, which are in remote parts of Australia, so that we can look at how we can improve our forecast services for mining regions. For future of data assimilation, we know that 4D VAR has limitations. It's difficult to get good results when you're simulating highly nonlinear observations like reflectivity. If you note the image on the right, this is an example of the observation values for reflectivity during an assimilation cycle. You can see that there is one extreme point, which is actually an embedded convective storm in a larger stratiform region. So it's not actually a data outlier, but a true reflectivity value. The assimilation isn't really able to capture that fine spatial detail. It just generally makes the model wetter across a region, as noted by the green line, generally here being higher than the blue line. which is the observations, but we don't actually capture real intense localized rainfall. We also suspect that it's difficult to assimilate both large-scale and small-scale information simultaneously. So we want to reconsider how we handle assimilation of large and small scales and perhaps treat them separately. We would like to look at using ensemble methods. One advantage of this is that it uses the full nonlinear model. However, the problem that we have is that it is too expensive to run a large ensemble, and this means that it's difficult to capture the uncertainty information that ensembles provide during data assimilation. In future, we expect to change to JEDI for our data assimilation software. This should enable us to more easily try out new DA methods and also look at assimilating new observation types and try to use better assimilation techniques for those observations. Next, with Sean Cooper talking about our convective scale ensemble.
Thanks, Susan. Yes, so hello everybody. I will talk about Access AE, which is our ensemble version of Access A. So we're also using a variable grid for this, as we can see on the right-hand side there in the image, where we have a 2.2 kilometer horizontally spaced grid for Access AE using 90 vertical levels up to 38.5 kilometer model top. The number of grid points is reduced on Access A, so we have approximately 500 million total grid points per ensemble member, of which we are running 12 members, also out to 48-hour lead time, similar to Access A, and we're also using the REL 3.2 physics configuration. So one of the challenges that we have among a few different challenges for Access AE is how do we verify such a large domain convective scale ensemble system? So at the moment, our approach is to break up the domain into a number of regions, as we can see in the image on the right, and do the verification over those regions. And also for specific high impact events, we will have different domains when we're verifying as well. So these regions that we've got are based approximately on climatology or weather types. Next slide, thanks, Susan. So far for Access AE, we've been able to run an Austral summer trial, sorry. These dates range from the 10th to the 17th of December of last year, and we've run 2 cycles per day, the 00Z and the 12Z forecasts. As mentioned earlier, we ran out to 48 hours. There were a number of notable weather events during this trial period, including TC Jasper, which we can see on the right-hand side with our simulated reflectivity images over part of the Access AE domain. There were also other severe weather events over different parts of the country, including suspected tornado in South Australia. There was fog in Melbourne. There was fire weather in New South Wales. Brisbane had thunderstorms. And there was a recording of 169 kilometre per hour wind gust at Archerfield Airport, also in Queensland. So for Access AE, we're currently running 2 different ensemble configurations. With REL 3.2, we're running the standard random parameter scheme, which is a stochastic physics scheme, but we're also running the extended random parameter scheme, which has additional microphysics and land surface parameter perturbations. Next slide. Thanks, Susan. So quickly having a look at some results here. This is a rock curve for the TC Jasper domain. In the top right-hand corner, you can see the little red square over which I've done this verification. And so rock curves measure the ability of the model to discriminate between events and non-events. So it's measuring the forecast resolution. The perfect rock curve would travel from the bottom left-hand corner to the top left-hand corner and across to the top right. And the area under the curve, if it's less than 0.5, the model has no skill. And if it's equal to 1, then it's a perfect score. As mentioned before, we were running 2 different ensemble configurations. However, the results for the 2 configurations are very, very similar, almost identical. So what I've plotted here are 2 different rainfall thresholds, the 100 millimeter and the 75 millimeter for the 6-hour rainfall accumulations. And these are against our radar gauge blended QPF product. So the area under the curve scores of exceeding 0.8 are very high, so they're quite good results. Next slide, please, Susan. We've also got the fraction skill score here. So fraction skill score is a neighborhood-based verification method where the rainfall is accumulated to the required period, in this case 6 hours. This verification has been done against GPM, so the rainfall, the model rainfall forecasts are regridded onto the GPM grid. Both the observations and the model are then converted into binary event, non-event fields for a given threshold, and the number of events that occur within a given window of each the observation and the model are calculated, which allows us to generate the fraction skill score. So if we just have a look, as we step across the different columns there, we've got different rainfall thresholds, 1, 4, 12, and 32. And we can see the lead times for each of those individual boxes at the very bottom of the image. And we've got the different window distances. So the take home from this is that any square that we see that is a purple shade of white has an FSS score of greater than 0.5, which is showing this model skill. So what I've got on the top is the control ensemble with a standard RP scheme. And on the bottom, I have the difference in fraction skill score subtracting the updated RP scheme ensemble with the control ensemble. Any shades of blue on the bottom show a benefit in fraction skill score for the extended RP scheme. So any red there shows that the control ensemble was better. Just note that the magnitude of the differences are quite small, but overall we're seeing good fraction skill scores for the two ensembles. Next slide, please. We've also done some surface verification. So this here is over the Southeast Australia domain. We've got the CRPS on the left there for the two ensemble configurations. So the CRPS is comparing the cumulative distribution functions for both the observations and for the forecasts. And we can see that the average CRPS is probably close to 1 degree Celsius, which is quite good. On the right-hand side, we've got the root mean square error in the top dashed lines for the forecast ensembles. The spread is in the bottom dotted lines, and the skill, which is the ensemble spread ratio with the standard deviation of the error, shows that the skill is at about 1. So the standard deviation of the forecast error should be the same as the RMSE if there is no bias in the forecast. But what it does show is that if we were to remove the model bias, there is sufficient spread in the ensemble for this domain over this trial period. Next slide, please. So we've also done some wind gust verification, and we can see on the left-hand side there that the new RP scheme has slightly lower mean error across the trial period for the tropics. And in the interest of time, I should just move on to the next slide, please. So there's a lot of ongoing work left for Axis AE. So we're about to commence an Austral winter trial from May 28th through June the 3rd. We're continuing our verification work. So at the moment, the rainfall metrics that we've computed include rock curves, reliability curves, rainfall distributions, and fraction skill scores. For the surface metrics verification, we've got CRPS, RPS, bias, error, spread, and spread skill. We want to understand how the performance in the different verification regions that were shown earlier, and then we need to evaluate specific high impact events. We will also in the future have a look at centering the initial conditions on the Axis A analysis and understand what the impacts on the forecast skill and ensemble spread will be, and also look at running the ensemble as a time-lagged ensemble. The next speaker is Chun-Soo Su, who will be talking about convective scale regional reanalyses.
Yeah, thank you for having me. So I'll be speaking to reanalysis. So I think most of you are no stranger to reanalysis. A particular well-known one is the Global Reanalysis Era 5. So it's about reconstructing historical weather records by combining physical models with observations. So BARA is the Bureau's effort on producing a high resolution and also convective scale reanalysis for our local regions. So in the earlier slide, you could also follow the QR code if you wish to follow on the details. So the BARA version 2, so this is our second go at it. It's made up of two systems, BARA R2 and BARA C2. So BARA R2, or R2 in short, covers a fairly large Australasia domain shown in the orange box in the map. So it simulates observations to provide 6-hourly analysis. So many types of observation are being used here, shown on the right. So also more, so that includes satellites and institutes. So also more local observation are being sourced and included in BARA. So BARA C2, or C2 in short, is the downscaling modeling system focusing over Australia. So that's initialized from the BARA R2 analysis. So that's shown in the blue box. So C2 uses the same models as the XSA that you've seen before and using the same size RL 3.2. So that we know that we are using a fairly well-tested model for this application. Next slide. So 45 years of BARA 2 has now completed, and there are many things that one can look at. I particularly single out 2 cases here where different reanalysis, R2 and C2, can provide very different interpretation of what had happened. So top right shows the Sydney hailstone back in 1999, the most expensive in the insured damage terms in Australia. And bottom right is the South Australian Blackstone event where there was 2 tornadoes and damaging winds knocked down energy transmission lines in the state and causing a statewide blackout. So here comparing R2 and C2, so looking at R2, they seem to suggest something happened, but certainly not the intensity and precipitations and wind speed that can be seen in C2. Maybe click the slide. There should be maybe additional illustrations. Yeah, so for the Blackstone case, there were actually nearby observation on that day, but none of them actually picked up the very high damaging wind speed. So that this example illustrates the shortcoming of our sparse observations in the region. So it's good to see that it showed up in BARA C2, even though the 4-kilometer models does not simulate tornadoes per se, but it simulated the high wind gusts associated with the convection induced outflows. Next slide. So now I just move on to briefly look at the added value of our regional reanalysis. So here shows the errors in the daily maximum temperature comparing against the Australian Climate Reference Network. So these are institute records that has been very, very carefully quality controlled. So here I've included ER5 and the first version of BARA R1 and R2 and C2. So in R2, you can see here clearly improve on the first version, which is good to see, and also downscaling with C2 further improves R2. Next slide. So this slide looks at the hourly rainfall accumulations. So here I've sampled 25 years of summer data over Sydney. So the summer is the thunderstorm season in the region. So here I plotted the normalized histograms, essentially the frequency of occurrence, as a function of hours a day in the x-axis and rainfall intensity in the y-axis. So C2 shows better agreements with the local scale observations in terms of intensity, as well as the diurnal cycles of the rainfall. So the gauges, the observations says that the wettest hours on average is about 8 UTC, while you can see that in the ER5 or R2, it appears to be 2 or 4 hours earlier. And C2 is able to show that it's indeed the wettest hour. And so that's an indication that C2 is better simulating the life cycle of storms. Next slide. We can also look at the rainfall extremes across the country. Here we've plotted the 10-year average of annual RX1H, which is basically maximum 1 hour rainfall for that year. So R2 clearly underestimates the intensity, with C2 showing a very good agreement with the gauges in capturing the extremes. Next slide. However, there are also rooms for improvements given we're doing a downscaling approach in C2 to produce the downscale reanalysis. Here we have looked at the agreements between reanalysis observation for instantaneous wind speed in terms of their PDF, so or the probability distributions. This is measured using the Perkins skill score. The higher, the better. So R2 and C2 both show higher scores than ERA5 at most locations. You can see that the text at the bottom right, they show figures. However, we also see that we also find that R2 winds are generally more accurate than C2 on average. And that's because C2 does not directly assimilate observations, just only using R2 analysis. Next slide. Our downscaling approach with the C2 also means that C2 models reinitialize every 6 hours for R2 analysis, and this is what we call cold starting. At cold starting, the models need time to spin up to develop the fine-scale features and processes. And this can lead to spin-up artifacts, and we can see that, we generally can see that in cloud and precipitations. So even after 6 hours of modeling spin-up, you can still see a bit of that. So there's a bit of that artifacts in the Bara C2. Next slide. So this is my last slide. So Bara 2 has been developed to support the Australian Climate Service. We are now looking ahead to develop our next version of reanalysis. Our focus will be the kilometer scale, convective scale reanalysis, actually assimilating observations at that scale. There are much room for improvements in our DA systems. Going to ensembles is important to provide uncertainty informations, sourcing more local observation, reprocess observations to improve analysis at that scale, and also tapping into rainfall observation to improve rainfall informations. We have benefited immensely to global reanalysis work, and we still need to make more use of it, since they are very skillful for the large scale. So modeling-wise, we need to further continue to improve it, resolution physics, and also, as you see, the co-starting approach has its issues, so we need to rethink how we do that. Finally, the synergy with machine learnings to enhance our reanalysis and also better support downstream machine learning research, particularly for weather predictions. So I'll finish it this part here. Thank you for your attention. Happy to take questions offline or online. Next up is Christian Starson. They will speak to the other important work supporting our Australian Climate Service. This is on the regional climate modeling.
Thank you very much, Junsu. Hello, everyone. Thanks for having me. Like Junsu said, I'm going to talk about our convective scale climate downscaling called BAR-C. The BAR-C model runs at 4.4 kilometers and is forced by our regional model that runs at 17 kilometers. And the regional model is nested in global models such as CMIP 6 or ERA5. BAR-C uses the version 13, REL 3.2, and is very similar to XSA, which has been talked about before. We're using greenhouse gases, volcanic and easy aerosol radiative forcing, and we're also using spectral nudging to, well, we started using it to address an issue that I will talk about on my next slide, but we also want BAR-C to stay as close as possible, actually, to its driving model. In terms of where we are with our climate downscaling, we have a few production runs that are currently going downscaling for models, but we're also doing a few trials and experiments because we found a dry bias in our downscaling. Next slide, please, Susan. That's the dry bias that I mentioned. So on the left plot, it shows you observations, and the middle plot shows you the difference in BAR-C compared to the observations. And what you can see is that in the northern parts of Australia, there's a very consistent dry bias that we haven't seen in our regional downscaling, which is the plot on the far right. We linked that to the monsoon trough being displaced. We found it's too far north, and that leads to not as much monsoon precipitation over the Australian continent. And we're currently investigating why this is happening with some sensitivity experiments. Next slide, please, Susan. But moving on to a few good things that we're seeing in our downscaling, and that is, for example, the diurnal cycle of precipitation. And here I'm showing you 3 different locations. The red line shows the regional model, the black line is radar, and the blue line is the convective downscaling, and you can generally see that the blue line matches the observations much better than the regional model. Next slide, please. That's a similar plot to what you have seen before. So here we're showing you the maximum hourly precipitation in the regional model to the left, the convective model in the middle, and observations on the right. And if you click one more, I think it masks it a little bit, and then we can see much better that the convective model, especially along the northeast coast and the east coast, much better matches the observations than the regional model does. Next slide, please. It's a busy slide, but here we're showing a tropical cyclone that is existent in the regional model and the convective scale model. And what we see generally, so the top plots always show you the convective model, and then the row underneath shows the regional model. And what you can see in the top two rows is the wind speeds. And you can see that this tropical cyclone in the convective model has a very nice eye wall, very nice wind features that are not existent in the regional model. And then if we go to the middle two rows, that shows you the rainfall, and we generally see much nicer behavior, or behavior that we would expect to see in a tropical cyclone in convective models. And then the last two rows show you vorticity. And we can see a very nice eye wall structure and vorticity ring in the convective model that are not existent in the regional model. We can also see on the right that shows you wind speeds compared to sea level pressure. And we can see that BAPA C has much better alignment with observations than the regional model does. So there, it improves on a lot of things. And I think that's it already, what I had. I think I was very quick.
Thanks, Christian. So I'm just going to take a few minutes to talk about our model developments and sort of future directions, and then we'll finish off. So we do need to keep working on developing the representation of some key physical processes in our convective scale models. This is really around improving convection, microphysics, and turbulence. And I think our big national pan-Australian models provide the ideal laboratory for testing these model developments. And noting that these models are also not only used for producing forecasts and predictions, but they're also used to generate the training data now for many machine learning applications. So we do need to continue to develop these models. And the reason why I think our models are great testbeds is that we have such diverse climate zones from the tropics to the mid-latitudes, including this arid region in the centre. We have really frequent and varied convective events, so tropical cyclones, severe thunderstorms, monsoonal systems, cold air outbreaks, extratropical cyclones, a really wide range of weather hazards, and pretty decent observational data to be able to evaluate these events. So we're happy to collaborate with people around sort of improving our models. We also have this pan-Australia convective scale ensemble system, which I think is pretty unique. And we could exploit that system to better understand the cause of model errors. So for example, here's an ensemble representation of tropical cyclone Seroja. So this cyclone underwent rapid intensification, and there were some of the ensemble members that were able to pick up that rapid intensification. So we could exploit those ensembles and really interrogate those members that captured that intensification to better understand the mechanisms behind that and use that information to better improve the model. Next slide, please, Susan. Another area where we need to do some model development, I think, is around introducing interactive aerosols into our convective scale models. So currently we use a prescribed aerosol climatology, and that means that for the recent, fairly regular smoke and dust events that happen in the country, we don't represent those events with our models. And when we have those events, we really do see that we have an increase in the errors, and you can see that in the plot down the lower left there. So this is the 2 metre temperature error. And when we had a really smoke event, lots of smoke haze over the city of Sydney for a number of days, we did see the errors in our convective scale models increase. So we're also, of course, not representing the aerosol cloud interactions since we're not running with these interactive aerosols. And we know that we can improve the cloud properties, so the cloud lifetimes, the brightness and the precipitation, if we have a good representation of those aerosol cloud interactions as well. So we'd like to look at developing the model to include interactive aerosols that could improve the accuracy, but also lead to a wider range of services, noting that sort of solar energy applications are really, really hungry for getting more of these accurate representations of cloud and radiative effects in our models. Next slide. Some other work that we're doing is working on developing regional coupled models, so collaborating with the Met Office to develop a coupled atmosphere, land and ocean and wave coupled model. And this is pretty important for Australia because our coastal zones are really where these feedbacks between the atmosphere, land, ocean and waves all occur. And it's also where 80% of the Australian population lives. Every year we have tropical cyclones that impact those coastal populations, and there's a lot of evidence that show that coupled models, coupling the atmosphere and the ocean and waves, do produce better forecasts of tropical cyclones and their intensities. So currently we're working on kind of looking at this from a weather perspective, getting the coupled model running, and we hope that that would potentially enhance the range of our forecasts and also improve the consistency of the guidance and warnings. Next slide. So finally, where we're heading towards is really, I think, towards one of these weather extremes, regional digital Earths. So we have these new national convective scale models for reanalysis, weather forecasting, including ensembles and climate prediction. So we are modelling the past, the present and the future, including these 1 to 2 day ahead forecasts to support decision making and rapid response. We do need to do some more model development to improve the accuracy and reliability of our forecasts and predictions. We're demonstrating the impact of adding the ocean and waves to the weather models, but that could then be expanded to the climate model as well. We have developed 300-metre modelling systems and looking at the benefits of running those sub-kilometre scale models over the kilometre scale models. So there is the potential to embed an on-demand 300-metre ensemble system within our national kilometre scale systems, really for looking at extreme weather impact assessments and forecasts as well. We have another team at the Bureau who at the moment are working with the Met Office to adapt the next-gen model to run more efficiently. I think there's also a need to better integrate observations into our modelling systems and to quantify uncertainty. And I think machine learning provides a really good opportunity there. So if you move into the next slide, thanks, Susan. So on behalf of all of our speakers, thank you very much for the opportunity to discuss our work. And we're very happy to take questions either now or later. Please feel free to email me and I can forward that on to the relevant speakers. So thank you very much.
Thanks, Charmaine. Thanks all speakers for a really fantastic talk. It's great to see how much progress is being made and also the breadth of progress in some different areas. And to hear about the technical challenges too is really useful. If anyone's got any questions, please post them in the chat and we can come to them sequentially. Whilst people are thinking of some questions, I had one around the Barra reanalysis. And it's quite interesting to hear about the possible use of large-scale nudging in that reanalysis. It's one of those things where you have a large domain which can produce its own kind of inherent circulation, but also might as a result produce biases compared to the global model or reanalysis. And I just wondered if you had any more thoughts on how you'd potentially use large-scale nudging in reanalysis to kind of constrain the model from drifting too far.
Chunsu, did you want to start with that one?
Yeah, sure. Yeah, so in fact, this large-scale nudging, this large-scale blending process is being developed for XSA. It's also similar to try to benefit from the large-scale and good quality analysis from the large-scale models. Yeah, so for Barra 3, we're thinking about tapping into what's being developed for XSA to do that, and then I think Susan can probably give a sort of a better description on what's the large-scale blending process being done in XSA. Susan, do you want to add to my point here?
Yeah, sure. So the large-scale blending technique that we're using in XSA is to take the global parent model, run a short downscaler, and then with the parent model and the XSA WOM running model, we would take the difference between those two fields, and that creates an increment. Then we'd filter that increment to remove smaller scale features. Then because we're running data assimilation, we would use that increment within the data assimilation step. And then we'd also apply that increment to the model forecasters in the incremental analysis update. And that effectively adjusts the model across the entire domain with information for the parent model. It's also possible to do the same thing, but without actually doing any data assimilation. So you would just take the parent model and create the increment and apply that directly to your forecast model without doing any data assimilation.
Yeah, so I was about to add to
information.
Yeah, that's right. About to add to that point. So we did also develop spectral nudging in the UN. Currently, we're using spectral nudging in the BAPA. So I think Christian alluded to that. So that's about filtering out the small scale and using the large scale information and having basic models solely steer towards the large scales, basically the filter state of the driving models at every model time steps.
All right, excellent discussion. Unfortunately, our time is coming to an end here. So with just a few minutes remaining, we want to thank all of our panel speakers from the Bureau of Meteorology again for their excellent presentations and for answering their questions. And also thank you very much for waking up very, very early to give your talk. Many thanks to all of you online for your attendance and participation in the chat, and also for those of you who asked questions.
Any feedback on today's event is very welcome. It could be sent to Rosie or myself or Huw, who was unable to join today. Contact email address is on the screen now. We're also very happy to hear from anyone who'd like to volunteer a seminar on a related topic, either from yourself or as a group of contributions from a particular organisation. We will update the webinar webpage with news of future events, looking to confirm plans for 2025 webinars shortly.
And we'll also inform all registered participants when the recording of today's event is available online. So please do feel free to share it with colleagues in your organizations and networks when it's available, and to encourage them to register for future events too. And in the recordings, you will see the slides with the emails addresses from Charmaine and group. So please feel free to reach out to them with your questions. I'd particularly like to thank James from the Met Office today for co-convening with me. And we also thank Charmaine, Belinda, Susan, Sean, Shunsu, and Christian, and to all colleagues who contributed to today's talk. Thank you also to Maureen and the WCRP Secretariat for their support, and to all of you online for joining. Bye all.